In this video, we are going to learn the limits of the ideal reactors and how they converge to one another by slight changes in the operational conditions. So let us remember what are the ideal reactors that we have explored so far. The first one is the mixed flow reactor. We have an impeller. The fluids come in and go out. And so far, we focused most of our attention to the steady state operation of the mixed flow reactor. So this is the mixed flow reactor, or a CSTR. In the other limit of the operation, I will write it over here, is the plug flow reactor. So I'm going to draw the plug flow reactor as such. The fluid element moves through the reactor just like a plug, and there is no backmixing with the fluid element neither in front of it nor behind. And the third reactor is the batch flow reactor. So let us put the batch flow reactor here. Let us see how we're going to link the batch flow reactor to the other two. This is the batch reactor. There is no flow. This is a batch reactor. There's no flow in and out of this reactor, and we have impellers to mix the contents. Now, in the mixed flow reactor, we have continuous and steady flow of the inlet and outlet fluids, unless of course there is a volume change, and volume change can be due to the change in the density of the liquid or the change in the number of moles of the gas components. This volume change can be present in both the batch reactor and also in the plug flow reactor. Under the conditions of the steady flow in and out of the reactor, this is a steady state operation, but there are situations that might require that we have an unsteady state operation. The first unsteady state operation condition is the startup of this reactor. During the startup, the reactor is empty. There is no exit, no effluent, but we are filling the reactor. So this is a semi-batch operation. If you compare the situation to the batch operation, we have one inlet, no outlet. Similarly, during the shutdown, we have no inlet, just the outlet. This is also semi-batch. So it is half batch, half continuous. The startup and shutdown conditions of the semi-batch reactors can be used to our advantage if we would like to improve the selectivity in a complex reaction network. When we would like to change the concentration of one of the species at our desire, we might add them gradually in a batch reactor. We might remove some of them from a batch reactor, or we might do both. This depends on the reaction network and their individual rate constants and their individual kinetic equalities, the orders and activation energies of the reactions. So when we just close one of the inlets or outlets, we are moving away from a mixed flow reactor. We are moving closer to a batch reactor, and we call this a semi-batch reactor. So this is one end of the limit of the ideal operation of a CSTR. Now let us see if we are operating a small-scale business and we really don't have the tank size required to process the amount of fluid that we are going to produce. For example, for the current social structures, we need to produce a lot of disinfectants, and we have a small tank to produce that disinfectant, or the volume of the tank is not sufficient to establish the sufficient conversion that we desire. But we have a few of those reactors at our disposal. What can we do? We can connect them either in parallel or in series. So let us take that CSTR concept and configure them in parallel. Now in this case, we take the V0, we divide it by n, however many reactors we might have. This is V0 over n, another one, another one, and of course each of these reactors have their outlets, and we have 1, 2, 3, and n of those. This is the nth reactor. Each of these reactors receive V0 over n volume of the reactant. This is the parallel operation, and when we are using these reactors in parallel, we have divided the size of the reactor by n, we have divided the volumetric flow rate by n, and each of these reactors have space-time that are equal to tau. Tau was V over V0, and it is also V over n divided by V0 over n, where n's cancel. So we are giving sufficient space-time as in the original reactor, but we have n reactors in parallel. So when we are operating n reactors in parallel, it really doesn't matter whether we are operating a very large reactor or n small reactors with V0 over n of the flow rate. On the other hand, we might have a series operation of the CSTR. Now this is semi-batch operation. N reactors in parallel, then I'm going to plot the n reactors in series. Now what happens if we operate those reactors one after the other? Are we going to get the same performance as in the parallel reactor? All right, so this is the first reactor, this is the second reactor, and so on, so forth. Then we have the nth reactor. Okay, so again, we have V0. Here, our volume is V0 over n, or V over n. the original volume of this reactor. Okay? And the space-time here is tau over n. Another tau over n, another tau over n. Now, when we arranged our reactors in parallel, we were able to establish the same tau. However, life changes when we connect those reactors in series, that each tau over n contributes differently to the performance of this reactor. And in the next video, we will derive the equations to demonstrate that this n reactors in series, in the limit of n going to infinity, approaches to the performance of a PFR. This is an important point that we have to keep in mind, because sometimes this concept helps us analyze very complex behaviors in a plug flow reactor without going through a lot of mathematical complexity. So we have now demonstrated, at least conceptually, the limit of CSTRs approaching to a plug flow reactor. Now let us look at this problem from another angle. Now we have a plug flow reactor, and so far we've learned that in the plug flow reactor, the fluid element moves through the reactor as just like a plug. There is no back mixing between this element and the element, neither before nor after that fluid element. Now, back mixing is the ultimate condition in the mixed flow reactor, that the impeller establishes the back mixing of the fluid elements so perfectly that there is a uniform concentration throughout. On the other hand, there is no back mixing in a plug flow reactor, and this fluid element retains its identity throughout the operation. So this fluid element starts with the same fluid package at the entrance of the reactor, maintains its identity throughout the reactor until the exit. In essence, this fluid element is behaving like a batch reactor. There is nothing coming in, nothing going out. That fluid element enters the reactor as is, stays there until the space-time allows it, and then leaves the reactor. Conceptually, very similar to this one. And of course, the mathematics of an ideal plug flow reactor and ideal batch reactor are also identical. Now let's take this plug flow reactor and introduce some deliberate backmixing. This plug flow reactor with its deliberate backmixing will look like this. So we have a feed stream, a product stream. We separate some of the product and recycle it back to the inlet of the plug flow reactor. So this is the recycle. So with recycling, now we have established some back mixing. We have taken some of the product, backed to the inlet, mixed with the feed, and the stream is now circulating through the reactor with some recycle. Now, the volumetric flow rate of before recycle and after recycle should be identical to ensure the steady state operation of this type of a reactor. Let's call this V sub R. In constant density, under constant density conditions, the volumetric flow rate here should be V0 plus V sub R. Also here, it should be V0, V sub R. Well, the mathematics, which we will deal with in the next video, the mathematics reveal that as the recycle ratio, what is the recycle ratio? There are several different definitions of the recycle ratio. Let me put them here. Recycle ratio. Okay, one of the definitions is VR, the volume recycled, divided by the total volumetric flow rate. V0 plus VR. Right. And the other definition is simply V0 over VR, depending upon how you configure your balance equations. Now let us take the first definition of the recycle ratio. In the limit of this recycle ratio, I will call this R. In the limit of this R going to infinity, in other words, VR becoming much greater than V0, all right, in the limit of, well, with this definition, R going to recycle ratio going to 1, all right, in the limit of the recycle ratio going to 1, we have plug flow reactor going to a mixed flow reactor. We're going to demonstrate that. Okay? So, how this happens? It happens because as the volume of the fluid traversing through a reactor increases, the conversion that can take place in that reactor inevitably decreases. As the conversion becomes lower and lower, the concentration difference between the inlet and the outlet of the reactor becomes smaller and smaller. In the limit that we have infinite recycle, nothing is coming out, is the limit of course, the nothing coming in and nothing going out, is the limit of the batch reactor. When we have minimal feed, minimal product, maximal recycle is the limit approaching to a CSTR. So now we have seen in this video how we take a batch reactor, convert it to a semi-batch reactor, then convert it to a CSTR. Then we have learned how to take a plug flow reactor and convert it to a batch reactor and convert it to a CSTR. Then of course we have seen conceptually how we can take n tanks in series and we say that the performance is equal to the performance of a plug flow reactor. So we are going to derive the equations to show you, to demonstrate you that the mathematical descriptions are also consistent with our conceptual descriptions. So in order to understand the behavior of a reactor, we sometimes use tracer studies. In the tracer studies, we feed our reactor. I will designate my reactor as a single black box without defining the characteristics of the reactor within that black box. I'm going to have an inert carrier gas or solvent. Let's call it inert background. Such as water flowing through a CSTR type of a reactor, or a plug flow, or any type of reactor. And we are going to introduce a tracer, also inert. Inert tracer can be injected by a syringe, for example. Let's have a syringe. And let's introduce a pulse of an ink. All right, this is a syringe with a needle. So we have introduced a pulse of an ink into an inert background, and we started to monitor the concentration at the exit. And the behavior of the concentration at the exit is going to tell us what is the type of the reactor that we have inside. Okay? So let us first derive the performance of the inert tracers through a CSTR or through a plug flow reactor. And then let's look at the performance, or let's look at the tracer analysis and try to deduce what's inside our black box. So in a plug flow reactor, when I introduce an inert tracer, there will be no interaction between the fluid package of the interest, and in this time the fluid package of the interest is this ink that is traversing through the reactor. There is no interaction of this fluid package with the fluid package before, nor the fluid package after. So this inert tracer for a plug flow reactor is going to look like this. So this is the time axis. I'm just looking at, I'm measuring the concentration of the inert tracer at the exit of my reactor. All right, so let me call this C sub I, concentration of the inert tracer. There will be no signal, none whatsoever, because this fluid package doesn't travel faster or slower than the fluid stream, okay? Until this fluid package traverses the whole reactor domain. In other words, until we reach the space-time of the reactor. And at that space-time, we will see a spike of this inert tracer. And after that, the signal will die out and we are not going to see anything. So this is the plug flow reactor behavior. Let us look at the CSTR behavior. In the CSTR, now we are going to introduce an inert tracer. Again, we have our syringe injecting the dye at this point, or let's inject the dye directly into the reactor. At time t is equal to 0. This is a perfectly mixed reactor. Let's have a little bit of artistic quality and the sharp and straight needle of our syringe. Immediately, this tracer is going to mix with the contents of this reactor, and the concentration will be CI0. Right? CI0. And let's write down the balance equations. For our mixed flow reactor or our CSTR. Let's start writing our balance equation. dNi over dt is going to be the rate with which I enters into the reactor. At the inlet, there is no tracer. We just dump the tracer inside the reactor, and that's it. We only have pure, blank, carrier background fluid flowing through the reactor. At the exit, we're going to have the same concentration that is inside the reactor flowing out with a volumetric rate of V0. There's no reaction term. So we have a constant volume reactor such that Ni is equal to V times Ci and dNi is equal to V times dCi over dt minus Ci times V0. That is equal to minus Ci times V0. We are going to take this V0 to here to make this term tau. We're going to do some rearrangement to obtain dCi over Ci is equal to minus T over tau. With an initial condition at T is equal to 0, Ci is equal to Ci0. The solution of this ordinary differential equation is Ci over Ci0 is equal to e to the minus t over tau. All right. Given this, I'm going to modify my plot a little bit. I will make this Ci over Ci0. All right. So this point will be 1. All right. So as far as our CSTR behavior is concerned, the behavior is going to be an exponential decay. So this is how we deduce whether we have a plug flow reactor or a CSTR. If you don't see any signal until a space-time t is equal to tau and we see a very sharp signal which dies immediately, means that we have a plug flow reactor. If we immediately see a signal which decays exponentially, then we have a CSTR. Of course, no reactor behaves like a PFR or a CSTR. Everything is in between, and our next video is going to help us understand how we can derive the expressions for a Tangson series type of a reactor. Now let us see what happens if we put a second reactor after our first CSTR. The first reactor, all right, had V and tau, so we recycled our board, so I'm erasing the V over N's. All right, now we have two reactors with equal volumes of V, therefore equal spacetimes of tau. At time t is equal to t0, we injected an inert tracer into the first reactor only, and the concentration at the exit of this first reactor is derived as Ci to be equal to Ci0 times e to the minus t over tau. Now, what will happen if I feed this stream into the second reactor of the same size? Let's see. So this is going to be my first reactor then, and this is going to be my second reactor. Now I'm going to index this as Ci1, and both reactors have equal spacetimes. So I'm writing the balance equation. Identical to a certain extent. V d Ci2 over dt time rate of change of number of moles of the inert tracer in reactor 2 is equal to the rate with which Ci enters this reactor. And you see there's a continuous flow of I, a time-dependent continuous flow of I out of the first reactor, which enters the second reactor. So I have V0, Ci1 that enters, Ci2 that leaves. What is the Ci1? This is C0 e to the minus t over tau. Again, this is going to be rearranged to have dCi over dt plus V0 over V is equal to 1 over tau C dCi2 Ci2, that is equal to 1 over tau e to the minus t over tau. At time t is equal to 0, now at the exit of the second reactor, nothing. Ci2 is equal to 0. Right? Initial moment is going to feed the first reactor, but this fluid has to flow through the pipeline to arrive at the second reactor before we can see any tracer output. Now, given that we have an ordinary differential equation, again, we're going to solve this through an integrating factor method. We're going to multiply both sides of this equation by an integrating factor of e to the dt over tau, the multiplier of the concentration term. This is e to the power t over tau. And when both sides of this equation is multiplied by e to the power t over tau, we get d over dt e to the power t over tau multiplied by Ci2 to be equal to 1 over tau. The e to the t over tau term and this term cancelled. When we integrate this equation, our function becomes, after substitution of the boundary condition and solving for the integration constant, also Ci2 is equal to Ci0 t over tau e to the minus t over tau. So, the first reactor exit concentration is Ci1 is equal to Ci0 e to the minus t over tau, or Ci1 over Ci0 is an exponential decay starting from 1. At the exit of the second reactor, Ci2 over Ci0 will have a t over tau multiplier. At time t is equal to 0, concentration is equal to 0. It will exhibit a sharp increase and another exponential decay. All right, so this is n is equal to 2. All right, so I am not going to derive the third, fourth, fifth ones, but let me generate a qualitative plot of single CSTR, 2 CSTRs, 3 CSTRs, 4 CSTRs, and infinite CSTRs. All right, this infinite is going to give us the plug flow reactor behavior. All right, and this tau, of course, this one, the first CSTR has tau, the second CSTR has 2 taus, the third CSTR has 3 taus, and so on and so forth, and the nth CSTR has infinitely many taus to deal with. For the n tanks in series, the concentration at the exit of the nth reactor is represented by the equation on the board. As you see, n is the number of identical tanks in series. This is our T over tau, as our T over tau here. Okay, so I think we should have a minus in front. Okay, and this term sums from 0 to n minus 1, n to the power I, divided by I factorial, multiplied by T over tau raised to the power I. So for the second reactor, we have 2 terms. For the third reactor, we have 2 terms. For the fourth reactor, we have 3 terms. For the fifth reactor, and so on and so forth. So it's a series solution, and this behavior is represented by the function. Now we are going to expand our understanding we have developed so far to the concept of the residence time distribution. I'm going to define this term as the washout function. And I will give the symbol w of t to the function, the relative ratio of the component I to the initial concentration, the relative ratio of the concentration of the inert tracer to its initial concentration. So let's start from here and define the washout function, Ci over Ci0. All right, so this washout function is going to be accompanied by the f function, which is 1 minus Ci over Ci0. So this gives us the fraction of the tracer at time t that hasn't left the reactor. This gives us the fraction of the species I that has left the reactor by the time t, and this is the fraction of the species that's still in the reactor that hasn't left. So I'm going to take the derivative of this. This is, of course, 1 minus wt df over dt is equal to minus dw over dt, and that is equal to 1 over Ci0 times dci dt. And I will label this with a small lowercase f, and I will call this the density function. So this f of t is the distribution, that we're going to deal with, that we are going to use to extract the characteristics of the unknown reactor by looking at the washout function. All right? So it is the first derivative of the washout function with a minus in front. That is f of t. Now, we have a few definitions for f of t. So first of all, integral f of t dt is equal to 1. All right? It doesn't depend on the initial concentrations. It doesn't depend on the system parameters. As a result, this f of t is a normalized distribution. Of course, integral limits is between 0 and infinity. This term is called the zeroth moment. The first moment is between 0 and infinity, t times f of t dt all right. So this gives us the mean residence time of the fluid in the reactor. I'm going to put a bar here in order to differentiate this residence time from this residence time. It's V over V0. This is going to be somewhat different. The second moment is going to give us the spread of the distribution. It is again going to be between 0 and infinity, t minus tau bar squared times f of t dt to be equal to, this is going to be the distribution squared. So for an arbitrary distribution function, all right, let's have an arbitrary distribution function like this. This is going to be tau bar and the spread full width at half max will be equal to 2 sigma, this sigma. All right. The reason that we are squaring the difference is to make sure that we have symmetry and not to have the values before tau canceling out the values after tau. So those three parameters, 0th, first, and second moments, will help us identify characteristic non-ideal behaviors in typical real reactors.